Hello, hello everyone. Thank you for joining today's webinar. I am Anna. I'm a project assistant at the Clean Energy States Alliance. The topic for today's webinar is energy storage in the Southwest. We'll be looking at two case studies from Albuquerque Public Schools and the Navajo Tribal Utility Authority. This webinar is a presentation of DOE OE Energy Storage Technology Advancement Partnership, also known as STAP. STAP is a collaboration between the U.S. Department of Energy, Sandia National Laboratories, and Clean Energy States Alliance. Before I pass this over to our moderator and presenters, I want to go over some quick webinar logistics, audio, all of that jazz. All of you are in listen-only mode today. We have a couple different options for how you want to join the audio portion of today's webinar. You can call in via telephone, or you can connect using your computers, mic, and speakers. If you'd like to minimize your webinar console, you can do so by clicking on that orange arrow you see circled on the screen right now. You can also click on that arrow to expand the webinar console. One thing you might like to do with the webinar console is to submit your questions to our panelists today. We're aiming to save between 15 and 20 minutes at the end of the webinar to be able to have a robust Q&A session. But please start submitting your questions as soon as you have them. Don't wait until the end. Our moderator, Todd, will be looking through it and picking out some questions early on. So please submit them as soon as you think of them. We'll get to as many questions as we can. We have a lot of folks registered for today's webinar, and of course, a lot of great presenters that we want to hear their answers and learn more about their projects. One last thing, we'll be posting this webinar and the presentation slides and the recording of this webinar to our website within 24 to 48 hours. Everyone will receive an email with the link to be able to view all this information afterwards. You should know the webinar, that's the URL link that's on the screen right now, cesa.org/webinars. That will include all the webinar recording information from today, as well as show all of our upcoming webinars. We have quite a few in December coming up. So with that, I will pass this over to our moderator, Todd, who is a Senior Project Director at Clean Energy States Alliance.
Thanks, Anna. Welcome to the webinar, everybody. This is another in our long-running series of STAP webinars, and I'll introduce what STAP is in a minute. I just want to first do a really fast introduction of Clean Energy States Alliance, or CESA. We are a nonprofit located in Vermont. We work with state energy agencies across the country. You can see many of their logos here on this slide. And we help them to develop and improve their clean energy policies, programs, and regulation in all sorts of technology areas. In this case, energy storage. If you could just advance the slide, please, Anna. So one of our long-standing projects is called STAP. It stands for Energy Storage Technology Advancement Partnership, and it conducted through a contract with Sandia National Laboratories under funding and supervision of U.S. DOE Office of Electricity. Now we have Dr. Zook here from DOE OE today to make some introductory remarks. As far as what STAP does, we facilitate these projects. You'll be hearing about two projects today. But there are many across the country. As you can see, a bunch of them are called out on this map. We help to bring together states, municipal partners sometimes, utilities, and other partners with the National Lab and DOE to jointly produce, design and build and operate these energy storage projects. And these are mostly large scale, although some are not, and you'll hear about one small one today, but mostly large-scale demonstration projects. Then we also conduct a lot of information sharing, such as this webinar. We do many webinars, and we've got, at this point, a decade of archived webinars on our website that you can go and view at any time or download the slides. We also produce conference presentations. We sometimes write or case studies and so forth. And we also provide direct support to state energy officials on their policies and programs that they're trying to develop around energy storage. Next slide, please. So that's it for my introduction. With one exception, I do want to thank Dr. Zook from DOE Office of Electricity and Dan Borneo, who couldn't join us today from Sandia, for making all this work possible. Next slide, please. I want to briefly introduce our speakers. Dr. Zook, as I said, is here with us from DOE Office of Electricity. He directs the Electrical Energy Storage Research Program at DOE OE and has for the past 2 decades. And in that program, he's developed a wide portfolio of storage technologies for a broad spectrum of applications. He supervised the $185 million ARRA stimulus funding for grid-scale energy storage demonstrations, and now partners with states, municipalities, and communities on numerous energy storage projects for grid resilience and energy equity, among other applications. His work has led to 11 R&D 100 awards, 2 EPA Green Chemistry Challenge Awards, and a Lifetime Achievement Award. And he's internationally recognized as a leader in the energy storage field. We also have Tony Sparks here from Albuquerque Public Schools. He's the projects manager for HVAC and energy projects at APS. He's also coordinator of the APS Water and Energy Conservation Committee and the APS Energy Team. So Tony is doing a lot, wearing a lot of different hats, and his teams have achieved impressive results and garnered numerous awards for their effective and progressive conservation strategies. He'll be speaking to the APS project today, along with Galina Kovchak, who is the CFO at OE Solar. I hope I pronounced your name correctly, Galina. She's actually the co-founder as well as the CFO, and they're headquartered in Albuquerque, and they have become one of the fastest growing solar companies in New Mexico. I seem to have a nosebleed, so I'm turning my camera off. My apologies. And I will just finish this introduction by voice. Henry Glahn is our final speaker today from Sandia's Energy Storage Technology and Systems Department. He's prior to this was the lead engineer in the high voltage electrical engineering team at Sandia, and previously worked at Public Service Company of New Mexico. So I will now pass this over to Dr. Zook for introductory remarks.
Hello, I'm Imre Juk, and I direct the Energy Storage Research Program at the Office of Electricity, Department of Energy. And I will talk today about these 2 projects. I will give a brief introduction. Both of these projects are solar plus storage. They are in similar location, meaning they are basically in the desert, and they were both commissioned in 2022, and they are social equity related. There are differences. One project is tribal, and one process involves the Hispanic community. One is small and one is large, and one of them is non-lithium, and the other one is a lithium project. So let's talk about the project in the Navajo Nation in Arizona first. We have a small project there, and we partner with the National Tribal Utility Authority and with Urban Electric Power. And what we have done is we have addressed the, well, roughly 18,000 residents which are still off-grid in the reservation. And they need to have electricity in their remote habitation. In the past, this was mainly done by little generators using diesel. Then there was an attempt to use lithium, and that works well, but lithium batteries and solar together have certain problems. Lithium ion still has maintenance problems, and so it was decided to try a new technology, and that technology is zinc-manganese oxide, as developed by Urban Electric Power. And you can see here the typical setup. Here is the photovoltaic panel, and here is the battery and the the EP units. And here you can see the crew. Well, basically, that was installing this particular unit. We have used NTUA throughout the projects. It's NTUA staff that did the electrical connections and put it together. And well, people like me are just onlookers. This is how it works. You can see a typical example, and you can see the solar coming up. That's the blue line. And it gets stored in the battery, the green line. And then that electricity is made available for the actual usage, which occasionally has big peaks, but generally is in a reasonably constant realm. Now, the capacity is about 3 kilowatt. The average load is about 150 watts, which is a lot less. That's the capacity of the system. And that leads to about 87 hours or 3.6 days, which are available as backup. So if there is no sun at all for 3.6 days, which might happen, but rarely, we have it fully covered just out of the battery backup. But in ordinary days, and particularly so in Arizona, the photovoltaic will make about 1 kilowatt available for daily recharge. So the battery is continually being recharged, and the system is essentially in a stable usage pattern. This project, first of all, we are already working at 2 more projects of the same kind. The zinc-manganese oxide, but there will be slight changes because we have learned something in the first installations, and we will incorporate that. We have other tribal projects, particularly Picuris Pueblo, which we are already beginning to do with the solar+storage project. We work with the San Carlos Apache. So far, these are all in the Southwest. And then a little bit further off, we have the Seminoles in Florida, and we have a village in Alaska, way off in Leeuwenhoek. And now to a different project, and that is the Atrisco Heritage Academy in Albuquerque. The thing of interest there is that it is 85% Hispanic. And it's also interesting because it's a school. And a school, of course, is not generally working on weekends or at night. So the daytime has a very large peak, and therefore during these occupied hours, we like to reduce the peak because that leads to demand charges. And so what we did is we installed a battery of 721 kilowatt. It's a 4-hour battery, so a fairly large thing. We can do the entire noon peak. And the contract was awarded in May of 2021. It took a little bit of a while because certain materials and components were not available, and it was finally commissioned in October of 2022. Oops. And you can see the rooftops. This is a very large school. You can see the installation of photovoltaics on the rooftops. And this, of course, is the school itself. Now, since these are equity projects, we have enlarged our equity offerings by creating an entire initiative, the energy storage for social equity. And in that initiative, 14 communities were selected to receive detailed technical assistance from staff at Pacific Northwest Laboratory. And of these, 5 communities will be chosen to partner in constructing a real energy storage facility. And that will be done with Sandia and with the same staff that has been active in putting together the Atrisco project and the Navajo desert installation. And with that, I thank you, and I lead over to the next speaker.
Thank you, Jeremy. My pleasure to be part of this team. It's an amazing experience that we've undergone here at Albuquerque Public Schools. So Atrisco Heritage Academy is one of 13 high schools in the APS district, one of the largest school districts in the country. And I have the dubious distinction of trying to be an energy manager for that footprint. And it's a huge footprint with a lot of opportunities for waste. So we continually analyze which sites need things the most, and it wasn't hard to come to a conclusion about Atrisco Heritage Academy High School. It's the largest school in our district and the state, as far as I know, with huge utility bills. In the summertime, the electricity bills are over $50,000. But the notable thing about that is that over half of those charges are demand charges in the summertime, meaning the availability of kilowatts at any given time is what's driving the bill to a large extent. So for pure financial reasons, we explored the idea of battery storage for peak shaving. And that means you would store energy during an inexpensive time, charge it off peak when energy is less expensive, and then strategically deploy it on peak during the day to reduce demand charges and basically save money. It didn't necessarily save energy, it saved money. And our goal was to reduce the daily peak demand to below the base rate that was included with our bill. For that side, it was 500 kilowatts at any given time. So if we could find a way to keep it below 500, we'd not pay any demand charges at all. In addition, this was a test case for replication elsewhere in our other high schools or some of our other large middle schools and elementaries to see if we could save money that way as well. Battery also introduces the opportunity for some other interesting things that I'll go into more later. But the bottom line for this for us was cost driven, and would it be cost effective to build this system? So in order to get there, we partnered with several people. And I became aware of the Clean Energy States Alliance right away, doing some initial studies on schools. Originally, we had looked at a different high school that already had some solar input on site, but we ended up going to Atrisco Heritage because it had the greatest opportunity to demonstrate the kind of savings that we were looking for and the use of this technology for making it go forward. It also opened up an opportunity to get financial backing from both the Department of Energy through Sandia Labs and our state energy office that supplemented this project to make it affordable to do as kind of a pilot. Plus, the expertise in this group is staggering. There are a lot of people that know a lot about this subject, and so we were able to share not only the finances, but the technical expertise. A win for everybody. So by choosing the contracting partner, OE Solar, that we did, they brought to our attention through some analysis what would happen if we used battery storage, PV solar in addition to the battery storage to optimize the payback. And it turned out that if you put about 850 kilowatts on there, which is enough panels for one per student at this particular school, we could reduce it from a 17-year payback with just the battery alone to less than 13 years by incorporating solar on top of it, because you're not only reducing the peak during the year, but you're providing free power during that time. The interesting thing about that 17-year goal, also the 17-year payback on the straight battery, was it was entirely dependent on what the current rate case happened to be with the utility. And if they changed the way they structured their demand charges, which they're prone to do, it could turn that on its head. This way we have complete control by having that free energy available during the day and the ability to discharge a battery whenever we want. So it, in essence, doubled the project's cost, shortened the payback, but provided a net savings of over $3.5 million over the life of the battery. And so it was worth taking a look at. I'm going to turn it over to Galina right now to tell you some of the technical aspects of the project itself, what we ended up installing. Galina?
Thanks, Tony. So this is an image of the actual installation of the Tesla Megapack in its enclosure. And we decided to go with a brick enclosure instead of a chain link fence because it has a little bit better of a design. The enclosure is 74 by 26 feet, and that's a 1,924 square feet. It's a 10-foot block wall, and the Tesla Megapack itself it's actually a Megapack 2, and it's 8 feet tall by 5 feet deep and 25 feet long. You can see in the picture that the BES site location of where it's located is off to the side of the school, and we picked that location because it's closest to the interconnection point with the utility. The battery itself is, as stated before by Dr. Zhuk, is 721 kilowatts, and it's 2,884 kilowatt hours that's deployed over 4 hours. Also, the size of the battery is about 56,000 pounds, so it's on a concrete foundation. And inside that enclosure, we have a automatic gate system to access for maintenance, and then we also have our switchgear and transformer, as well as the Tesla Megapack. Tony? Oh. And then here's another picture of the Tesla Megapack, so you can kind of see the scale of our workers there against the height and the size of the battery. And the Megapack is a powerful battery that provides energy storage and support. We also have a battery meter on this site, and that measures the power output from the battery. This helps with the OptiCaster to optimally dispatch battery system power. So that battery meter is required by Tesla for that dispatch of power. And then we have this Tesla site controller, which interacts with the Megapack, collects feedback data, and runs to optimize the system's operation. In addition to the standard Tesla site controller enclosure, is built in for redundancy at the standard Tesla site controller level. The OptiCaster, as I mentioned, is the site controller software. Is designed to maximize economic benefits for grid-tied customers. The OptiCaster forecasts load and solar production, optimizes battery dispatch to reduce electricity bills, and maximizes consumption. I will note that our battery system that is at Atrisco does not intertie with the solar system. The system is two separate systems, and the BES is connected with the radial loop, a 15 kVA radial loop around the school itself, and the solar runs into and interconnects with individual buildings, which I will go over later. But the solar does not charge the battery on the system, which is something that a lot of people are a little bit confused about. So I just want to make sure that that is crystal clear. We also have a power hub, and this is the Tesla software solution for monitoring the performance and analysis of distributed energy assets. We also have a site meter, which measures power pulled from the utility grid, which helps with deploying that energy and then charging the battery at night. We also have a switchgear, and the switchgear is used to control, protect, and isolate electrical equipment. The switchgear is used both to de-energize equipment, to allow work to be done, and clear any faults downstream. And finally, we have a transformer that steps down from the 12,470 utility voltage to the 480 volt power that's used for our system. Sorry, Tony. So basically the Tesla Megapack benefits is that it's a turnkey system. The Megapack comes completely enclosed. It has its own fire suppression system within the Megapack. So that helps from having to install individual batteries and individual inverters and systems. So that turnkey portion of it really helps quicken the installation. As I mentioned, it has an integrated heating and cooling at the cell level for the Tesla battery to keep everything cool and to mitigate fire. Another great benefit of the Tesla battery that we found for this project was the software. So that way it can learn as the system is in operation for when to deploy energy and when to store power. And we also have it as module level DC to DC converters that can keep the system running uninterrupted, which is also a huge benefit. And then obviously reducing carbon emissions. And then let's get into the PV system. So this is the actual PV system installed. We actually installed over 5 different roof planes. And you can see here that it's a little bit different than the design that Dr. Zook showed. We found some roofs that weren't going to be optimal for the solar. So based on the age of the roofs, so we had to look at our design. But this is a great overall picture that you can see the solar there. Our PV system is 850 kW DC, and it's over the 5 buildings. It's in 15 separate arrays with 4 separate interconnection points. Each one interconnects at the building's main service panel, as I mentioned, and it produces 1.3 gigawatt hours annually. We used REC 385 watt modules, and as noted by Tony, there's actually 1 solar module per student, and we have 16 inverters total, and those are SMA Tri-Power 50 kW, and they're also installed with Unirac RM10 ballast mounted system, which you can see in this picture. The biggest benefits of the solar is the cost savings that Tony mentioned, and load management. It's also going to help reduce that high demand during peak times of the day when kids are in school, and then also that we have the installation sets an example for future generations to bring new clean technology and gives great environmental benefits. So in project summary, just for the installation of the project, the overall cost was about $3.2 million. We also had the financial partners that Tony mentioned. Excuse me. And then we also have the cost savings and the ability to look at the system as maybe a power shelter in the future to have the solar run the battery and look at that in a future project, but that's not currently how it's set up. And then also with reducing carbon emissions. Back to you, Tony.
Thank you, Galina. And Anne, if you get the chance to give me control again, that'd be great. So it's just a coincidence that there's one panel per student. We didn't plan it that way, but it gives us a metric for planning new schools that potentially you can do a back of the napkin estimate by knowing how many students are in the building, how many panels you might want to put on the roof. So I was going to reiterate some of the benefits from the owner's perspective as a school district. And, you know, our objective is really clear, to educate people, but we have to do it in a sustainable way for good stewardship of the public's money. So not only cost savings, energy savings is an important aspect of what we're trying to do. And the solar aspect added to the battery definitely brought us an opportunity to do energy savings as well as cost savings. For our large footprint, understanding how this could be duplicated in other areas was an important aspect, and the things that we have learned and will learn from this system will teach us how to do it better in the future, not only for us, but for other school districts. But obviously a huge aspect of this project is the benefit of education for students on site, for the community, for people to understand how action needs to be taken now to mitigate climate change. We all can do a part, and we have to find creative ways to do it. So part of our project here includes an on-site learning lab in and around the enclosure where the battery is. We'll have ground-mounted samples of solar panels and an inverter, plaques that describe how the system works, and teachers from all over the district can bring classes there to witness firsthand what a system like this looks like, understand the scale of what it took to get there. Obviously, that's of primary importance to us. In general, this also makes the whole community aware of, through the exposure to this system, aware of what APS is doing as a public entity and what others should consider doing as individuals, private and public, to make the contributions we all need to make to climate change. So these are some of the benefits I see as an owner. More to be discovered as the project continues. One of the really great aspects that came from adding the solar to the battery was that we now had the way to address the possibility of resiliency at this site. And as Dr. Juk mentioned, this is a large Hispanic, but not only Hispanic, a large disadvantaged population. 100% of the students qualify for free or reduced lunch through the federal criteria. It's 16% have English as a second language. Many other aspects that I won't go into, but this was a great opportunity to test resiliency in a disadvantaged community. And so we took that to task. So the PV allows you to island, meaning disconnect from the grid, because you have a power source when you're not connected to the grid and a battery to store it to use it when you need it. That's an important component. As part of the existing project, then, we have conducted a feasibility study to figure out where on the campus you might create this power shelter. There's not enough battery to run the whole campus all the time. So we chose one of the larger community type buildings that happens to house the gymnasium, the library, and the cafeteria, all large gathering spaces. And our plan is to find the critical loads within that space, and then as part of this project, devise our implementation plan for rolling it out as an actual resiliency hub. So our next task is to find funding to make that happen. There are other sources to make it happen, but it's built into the project, the anticipation of doing that in the future. many opportunities opened up because of adding the solar to the battery. So I wanted to kind of close with some challenges that we experienced and a challenge to other entities, including school districts. If we can lead the way, you can too, and will you? So some of the challenges that we experienced along the way were working together with the utility that hasn't really done projects like this much. You don't find school districts that put large solar and battery installations on their buildings. And they don't know how to deal with interconnecting it to their grid yet. So a big part of the pains that we experienced have been working with utility to interconnect it in a way that's acceptable to their side without breaking the bank on our side. And that is an ongoing thing I might mention. Obsolescence is always a possible challenge. Could these pieces of equipment that we put in or the technology that drives them require updates or become obsolete sometime during the lifespan of this project? And it's something you need to look at and be prepared for. Always, as my boss will attest, being the early adopter means you pay premium price for the project. And without the supplemental funding from DOE and the state, I doubt this would have happened for us. But as we figure out what works in this process and how to build efficiencies into it, it becomes possible for other entities to follow suit in a more efficient and affordable way. A huge piece of any type of strategy that you undertake is equity. And with our large district, we have communities throughout that are of all financial levels and whatnot. So we have to be able to distribute this in a way that works for everybody, is equitable, and doesn't exclude anyone. So we're looking at ways to roll this out throughout the district, not just in the disadvantaged areas, but in all the areas. The other thing that's required, and this is critical, is leadership. You have to find someone who will own this thing and be the champion from the beginning. You have to have someone not afraid to speak up to upper management to make it happen. Hold on a second. Okay. I had some noise in the background. I apologize for that. So it starts at the top and it starts at the bottom and it meets in the middle. And it takes a leader, a champion in there to make that a reality. So those are the kind of things that we experienced. And I would put out to other districts and other industries a challenge to take the step, to bite it, to find people and partners that will work with you to create it and help fund it and make it happen. And then you can be a big part of the solution that we're all looking for. And with that, I will turn it over to our next speaker, which I didn't mean to do that. There you go.
No problem. Thank you, Tony. Let's see. All right. So, hello, everybody. My name's Henry Guan of Sandia National Labs. As Todd mentioned, I'm an electrical engineer / project engineer on the demonstration projects team in Sandia's Energy Storage Department. And so today I'm going to present on one of our more recent projects, which is the deployment of a rechargeable zinc-manganese dioxide battery storage system on the Navajo Nation. All right, so demonstration projects team, what's that? So just a real quick overview, what do we do? We support different partners in the deployment of energy storage. We work with owners, operators, vendors, state energy offices, academia, and others to deploy systems. Oftentimes our partners, they're folks who are interested in energy storage but haven't maybe dealt with energy storage before, or they're familiar with energy storage but haven't really had a lot of experience implementing a project, going through the project process, so we provide them support for that. Our program is supported by Dr. Zook and DOE Office of Electricity, and we provide valuation, techno-economic analysis, as well as the project deployment support I mentioned. All right, so for this project here are the deployment partners. We partnered with the DOE Office of Electricity, the Navajo Tribal Utility Authority, or NTUA. They're the utility that's the provider of water, gas, and power for the Navajo Nation. and Urban Electric Power, who's the manufacturer of these rechargeable zinc-manganese dioxide batteries. So the objective for this project was to deploy a system on the Navajo Nation at an off-grid site and learn how these batteries can help folks who don't have power. For the partners on this project, this deployment will provide valuable info on this type of application. So off-grid, not connected to any power lines, daily cycling of batteries, and then for like the NTUA, how these batteries can potentially help reduce operations and maintenance costs. This is an important aspect for the NTUA as they have limited resources when it comes to maintenance. And most importantly for the homeowner, of course, the system will provide power for them. And so as part of this project, we'll be installing a data acquisition system to monitor performance, conduct lab scale testing of the zinc-manganese oxide batteries to kind of predict how they will perform, and then compare and validate the performance. Oops. All right, so the deployment is in Northwest Arizona on the Navajo Reservation. So for those that don't know, the Navajo Reservation is the largest reservation in the United States. It covers about 17.5 million acres and spans across 4 different states. And so to give you an idea, the area of the reservation is greater than that of the states of Massachusetts, Vermont, and New Hampshire all combined. Because of the large and rural nature, there are many homes without power. I think previous estimates were about 18,000, and more recent figures, 15,000 residents that don't have power on the reservation. This is largely due to just being cost prohibitive to run line extensions out to certain homes because of their distance from infrastructure, or just the lack of power infrastructure in the area. And so the nearest town or census designated place for this deployment is called Delcon. According to 2020 census data, there was a population of 1,235 people within Delcon, but many more people in the greater area. And so the home where this project was deployed is about 2 miles outside of the town itself. Now keep in mind, I said many more area, but they're spread out, many more people in the area, but they're spread out to a large geographical area. All right, so an overview of the system we deployed. So the system consists of rechargeable zinc-manganese dioxide batteries, as mentioned. So these are very much like the chemistry in your typical household AA batteries. However, unlike those batteries, these have the ability to recharge due to the inclusion of patented additives from UEP. These batteries have been tested by UEP to operate at more than 122 degrees Fahrenheit and are certified to pose no thermal runaway risk. These batteries are also maintenance free and don't require refilling of electrolyte. So these are all features that are of great interest to NTUA, where, like I mentioned before, resources and personnel for maintenance are limited. The system consists of batteries, an off-the-shelf Outback FX series inverter, an MX series charge controller, and then a custom data collection system that was assembled at Sandia using off-the-shelf equipment. The system is rated at 3 kW and 13 kilowatt hours and consists of 10 cells per module, 4 modules per string, and 3 parallel strings in the system. So on the right, you see some pictures of kind of what all these parts and components look like. You know, the diagram is kind of small, but it's showing the connection of the battery system to the electronics and then out to the residents. So here's some additional photos from the system that was deployed. On the upper left, we have the batteries inside of the battery compartment of the enclosure. On the upper right there, we have one of the modules with the cover off showing the individual zinc manganese dioxide cells. On the lower left, you see the solar panels that feed this battery in home. I think you saw something similar in other pictures earlier, but there are six 300-watt solar panels. And on the lower right, you see all the electronics for this system here. So the inverter, the charge controller, there's a human interface as well as the data collection equipment. All right, so system integration. The integration of the system was performed at Sandia Labs. So the batteries and the enclosure were shipped to Sandia and assembled at our energy storage test pad. This is a facility here at Sandia where we have grid connections and area and space to test various types of battery systems. Here we worked with UEP on optimizing the charge settings for the batteries, ensuring that any modifications that needed to be made to the enclosure for assembly were performed, and we performed function testing of the system as well. So the system was deployed to the site in May of 2022. So they were successfully placed into service. So I have their early estimates were about 8 to 12 days, as Dr. Zook mentioned, about 3.6 days based on current estimates of power being able to be supplied to the home there. This is the first of 3 demonstration deployments that will go to off-grid homes on the Navajo Nation. So in addition to the system deployment, Sandia is performing laboratory testing of the cells to help predict performance of the system. So this information will help us compare and validate the batteries as mentioned earlier. And so cycling of these cells in the laboratory is performed using solar aging protocol, and it simulates a year of cycling per round. And so as mentioned, UEP mentioned that these batteries can operate up to 122 degrees Fahrenheit, and we're seeing that these cells are optimal in higher temperature environments. And so we're continuing to evaluate and assess these batteries. All right, so speaking of the field data, here's a snapshot of some of the information that we're collecting. So this information will be compared to the information previously mentioned from laboratory testing. And so one of the primary goals for the laboratory and UEP is to really evaluate how these operate in off-grid environments. So data for this system is collected, as I mentioned earlier, through a data collection system assembled by Sandia here using off-the-shelf devices. So those devices consist of a cellular modem, and a Raspberry Pi device, and the code in the device is what collects the data and sends it to an influx database where this visualization can be performed and data collected for later analysis. And so this deployment, it's been a great project for collecting this type of information. More importantly, besides the kind of laboratory assessment and value of this project, I think being able to provide power to an off-grid home is extremely important, and having options for NTUA to consider when looking at different types of battery systems for these off-grid deployments is very valuable. And so we look forward to the next 2 deployments with our partners. And with that, I think I will close this up. Thank you all very much.
Great. Thank you to all our speakers. I think we have a few questions from the audience, and we have time to address more. So if you are listening and you have questions, please go ahead and type those in. And if we could have the speakers come back, turn on your cameras, please. And we will start to address some of the questions. So first question is, I think this was in regard to the APS system. The question is, what are some of the specific issues with using lithium-ion batteries for solar storage? That's a pretty
Henry,
broad
that might be
question.
Henry,
Anybody?
can you address that, or Dr. Zook?
Well, lithium-ion batteries are very commonly used with together with solar. In fact, it's probably one of the most popular type of installation for energy storage systems. It's not quite obvious what the question is about. But one of the aspects which we need to address is, of course, the air conditioning system, because lithium ion will need air conditioning, and that represents an extra burden on the efficiency of the system. And particularly when you're dealing with very hot environments like desert environments or very cold environments, you have to you not only have to install an air conditioning system, you also have to, you will have reduced efficiency on the system. The other one is, of course, that you do need a fire suppression system, which, for example, you do not need for zinc-manganese oxide. And this system is important because on occasion, it has happened that lithium-ion batteries have overheated and gone into, well, a fire event. And that can be quite serious, and therefore you need a fire suppression system. And there's a number of them available of various degrees of effectiveness. One of the important things is to vent the system, and possibly to install a system that will automatically open the doors of the cabinets so that you avoid an explosion situation. In the particular application that we have here at Atrisco High School, there are the cabinets, and the cabinets are surrounded by a wall, so you're not dealing with a small building that the batteries are in. This is an application which you might find frequently in the actual applications of solar plus storage. And so the safety has been considered as much as possible. Otherwise, lithium ion is a quite suitable battery, and its footprint is small relative to other batteries, or smaller, and it is fairly safe provided you make all these cautious things that will make it safe.
Okay. Well, we have a few questions that are sort of along these lines. I'll just read one. How do the zinc manganese dioxide batteries compare functionally with lithium-ion batteries regarding capacity, lifespan, cycles, sensitivity to depletion, etc.? This is a big question. Obviously, they're two very different technologies. So, anyone want to jump in on this?
So very, very broad question, but I think in general, speaking in general terms, lithium-ion has the highest density of current battery technologies. So in terms of charges, cycle, and just pure output for size, lithium-ion you know, it's really your optimal technology. However, the zinc manganese oxide batteries, you really have to take into consideration your deployment environment. So for this specific deployment here, it was in a very hot, deserty environment, places where lithium-ion batteries don't perform as well. As a matter of fact, we've seen some issues with lithium-ion battery deployments in hot desert environments that are not climate controlled. You know, like this deployment environment where electronics can overheat, system shuts down. And so that, and then from the safety perspective, as Dr. Zook mentioned, there's additional burden on safety systems, fire suppression systems, in being in a remote area where you don't have readily available fire response. It can be hours away. You know, there's importance placed on that. So safety and deployed environment is a big consideration for these types of batteries.
We also have concern for the future there because the supply chain for lithium has problems with it. And we'd like to have more technologies that we can have access to, and particularly technologies which can be manufactured in the United States. And this particular zinc manganese oxide is being manufactured here in the States. And we have ample reserves of zinc and manganese that we can access. And therefore we are not limited to the current supply chain of lithium batteries, which, as I mentioned, has certain problems.
Okay. Are there any projections on performance of rechargeable zinc batteries in the variable and very cold settings? And we have another question similar to this. Henry, would you consider insulating/heating the batteries in cold conditions to overcome bad cold weather performance?
So we do have some information on cold weather performance, and we are seeing they perform better in hot environments. We're still collecting information, obviously, as this is we're just getting into the cold season of the deployment here. As far as insulation goes, insulation was specified for this enclosure, and so you know, the temperatures inside the enclosure are a bit higher than ambient temperatures. So insulation was considered. Hope that answers the question.
Okay. Are the flow batteries particularly sensitive to temperature, or more so than lithium, for example?
The zinc manganese dioxide batteries, I think there are some temperature sensitivities in the colder range, whereas lithium ion, it's kind of the opposite. You have temperature sensitivities going into the higher temperatures.
Okay. Well, here's another temperature related question. This is for Tony, I believe. It says, what percentage of your summer load is air conditioning? And did you analyze ice storage for peak load shaving?
Okay, two-part question. So we did a full analysis of energy use month over month for a few years to come up with the sizing of the system. Our heating season starts kind of November-ish and goes through March-ish. And then air conditioning is required beyond that. But in some of these larger buildings, such as Atrisco Heritage, it's so big it actually requires cooling kind of all the time. It's with load in there, even during the middle of the winter, sometimes we require some cooling just for load purposes. We have explored ice storage. I think it's a feasibility based on available space and whatnot. Space is a premium for us at APS. We have no ground mounted PV to speak of. We've got 30 sites with rooftop and a couple with parking structures, but the real estate has to be reserved and flexible for changing demographics. When populations move, we have to add more and take away from more, and sometimes a field becomes a building and vice versa. So we typically don't look at ice storage for not having a place to put it, unless we could put it underground, which anyone who's worked in New Mexico soils knows it's really difficult to do. The ground is really hard over here. Hope that answers the question. Galina, do you have any other comments on that?
Yeah, ice storage, of course, is an option, and it is applied particularly in urban settings where you might not want to put lithium storage into it. And ice has a very large specific heat when it changes to water, and essentially you have a big tank which gets transformed into ice during the night with cheaper electricity, and then in the daytime you can use it directly for air conditioning, and this is another way of saving demand charges and reducing the peak, which is something which again in the future is going to be of increasing importance.
Okay. Yeah, we should probably note that in terms of peak demand reduction, there are many things that building managers and owners can do. Obviously, energy storage is what we're talking about today, but so we already discussed ice storage. There's things like controllable thermostats and water heaters, and there's all kinds of EV charging and so forth. You can connect these systems and have them respond to a signal from the utility, and thereby reduce peak loads. And so we probably won't get into all that other stuff because this
Todd,
is an energy storage webinar.
I would like to make one more comment from the school district's
Sure.
perspective.
Go ahead.
The vast majority of our buildings are already built. We very rarely build a whole new school campus. So everything we're doing is usually a retrofit. And that's why something like ice storage is harder to do on an existing building than it would be if you had new construction, especially if maybe a high-rise building or something like that, a place to put it. So that's another reason that we are looking at strategies that can work on existing campuses.
Right. Okay. We have a couple of questions specifically about the UEP battery. This is the Navajo Tribal project. One is what functional tests were performed on the UEP battery, and the other one is how many cycles are these batteries good for?
So the functional testing that was performed was to validate the charge set points, voltage set points on the inverter. And so that was done using simulated loads at the energy storage test pad after the entire system was assembled. So when it met the threshold to start charging, we wanted to make sure it would charge, and when it met the top of voltage, we'd make sure it would stop. In terms of cycling and cycle life, so I believe in previous applications where these are in, I think, a type of UPS type of application, it stated about 8 years worth of cycling. I think in our laboratory testing, we simulated 2 years worth of cycling. I think that's the max we simulated out to. So, actual cycling performance, that's one of the items that we will be monitoring and trying to validate as part of the deployment.
Okay. Back over to you, Tony and Galina. At the Albuquerque school, what were the downsides to connecting the PV to the battery? Or I guess, are there any downsides?
It wasn't necessarily downside. I think it was logistics. I think Galina would agree. It was how this campus is laid out with a big radial loop for power around it. and each building has a medium voltage transformer that pulls off of the radio loop to feed that building. And there were like 6 or 7 different buildings on the campus. So when you're doing roof mounted PV, you want an interconnection point. It's easiest to take it inside the building to the panel that's fed by the medium voltage transformer rather than to try and take it out to the radio loop somehow. But we want the battery on the whole loop for the whole campus. So I think, Galena, does that sound right? That's kind of the way we arrived at that. It wasn't a downside, it was just a logistic necessity.
Yeah, I would also just note that it was also the way the RFP was written as well, that it was very specific for peak shaving. So the solar was an additional cost saving benefit. And that's why we kind of also for, like you were saying, Tony, for where things were located on the site, it made the most sense to interconnect the solar at each building.
Okay. We have a couple of questions, and I'm not sure what this refers to, but I'm just going to read the question. Dr. Zook mentioned there was a battery issue with the Navajo installation. Can you explain what the issue is? I'm not sure what that's referring to, but maybe you know.
No, I think, as a matter of fact, Henry can explain that better. It refers to the difference between the lithium-ion installations and the zinc-manganese oxide installations, and the problems we have had with some of the installations of lithium-ion.
Yeah, so in that respect, lithium-ion batteries deployed in that environment had issues, I believe, with electronics getting too hot and just the overall battery system getting hot. They're installed in enclosures that don't have a controlled environment. So, basically no air running through it, no cooling, etc. And so those are kind of the issues with deploying a lithium-ion system in that type of environment.
Yeah, and for example, the owners had to get up in the middle of the night and open the door to the cabinet, and which was sort of in the shape of a small outhouse, if you wish, and had to open the door. And one of our concerns was the owner mistaking one facility for another facility.
Well, I'm going to let that one go. I don't think I can add anything that's appropriate at the moment to that. But yeah, so here's a question that's sort of related. What other technologies are being considered for supporting native or remote communities?
Well, I think I'll talk more to what's currently in use. So with the NTUA, they have flooded lead acid systems, they have AGM systems, and lithium-ion systems. And so this was a battery that I think is kind of similar to lead acid type of systems. So in terms of ease of installation, it was kind of compatible, and it requires less maintenance than some of their lead acid systems, particularly the flooded ones. From their experience, NTUA is having to refill electrolyte in the flooded batteries frequently. And as I mentioned, their limited resources, I believe, speaking with the electrician who installed the system, they had one low voltage electrician for that entire district, and sometimes he would have to drive 2-3 hours to one job site. So as you can imagine, as they deploy more and more systems, or having more and more aging systems they have to maintain, it takes up a lot of time. And so evaluating this particular technology was looking at something that can replace those flooded lead acid batteries or other batteries as they reach their end of life, and be less of a maintenance burden.
Yeah, and you have to remember that not all the roads are paved, and Maintenance involves driving along dirt highways, and well, it's rather bumpy. And it takes a long time because, as Henry mentioned, it's the size of Massachusetts, Connecticut, and Rhode Island put together.
Yeah, we've it's an interesting topic. Is what's the best technology for really remote areas where maintenance either needs to be done locally or it might have to wait. And that's an interesting topic. We talked a little bit about safety. Somebody is asking whether lithium-ion battery fires are more difficult to extinguish than other types of fires, and what type of hazardous gases are released. And if we're going to address that, I'd also like to just address the issue of general fire safety and fire department training as well on these projects.
So let me address that part before we go to the technical part, because it was important. Being on a school campus, we cared a lot about the safety. That had to do with where we located it, how we oriented it, what the wall was like. But we also had to engage with the local fire authorities to devise a plan, a fire safety plan in case it's needed. And it's also a training for the occupants of the building. So all that goes into the piece from our perspective. Should something like that occur, everyone knows what they need to do and where they need to go. And the technical side, I would defer to others.
Yeah, lithium fires are definitely more difficult to extinguish than other fires. In fact, the current wisdom is that if you have one, just let it burn, but make sure it doesn't spread, and that you keep people away from it. And you just have to take potluck in what happens. One of the issues, by the way, which has come up recently, particularly in New York City, for example, is that people buy themselves little scooters that are electrically powered and bring those scooters up into their apartments, and they have something like, I believe, 60 fires or so of that type that they have to deal with. And the only way to deal with it is to just let it burn to an end, because even if you try to extinguish it, it will rekindle from the chemical composition. So, they are not necessarily that frequent, but on the other hand, they are serious.
I would mention one of the features, one of the features of the Tesla Megapack was that it's in compartments that are sealed from each other thermally, so that should one catch fire, it's not going to spread to the whole
right
enclosure.
Very important to do that.
I'd say, just to add to that, the difficulty in extinguishing often is the reaction that causes the fire happens within the cell. And so if you're spraying agent, putting water on it, it's cooling the outside, but not directly contacting the material that's reacting. So, the containing the fires or letting it burn out is often the solution. Making sure that heat doesn't spread to other cells and cause, that reaction that causes the fire in other cells.
Yeah, and that was one of the reasons that we spec'd the Tesla for this project, was because it had a fire suppression system already in it as well. So.
Yeah, I was going to note that as far as I know, all of these larger scale battery systems are now installed with fire suppression systems inside the container, and other preventative measures such as what Tony was talking about with compartmentalized sections And there's a fellow at Sandia who has come up with a system that automatically opens the doors in case of an overheating event. One part of this question was about gases, and I think it's becoming clear that you have to, in case of a fire, you have to vent the gases and not let them build up inside the container, because that causes other problems. So there are ways to deal with all of these things. And, you know, I should also mention that I don't know if we showed it, I can't remember on the slide, but whether you could see it, but there's a wall that separates that battery from the school. Just physical separation. There's distance and there's a wall. And, you know, this is not rocket science. I mean, we have developed such measures because other energy sources have similar problems. Fuel tanks combust, gas pipelines explode. You know, electrical boxes occasionally cause fires and so forth. So there's ways to deal with these things. Okay. Here's an interesting question. Has anyone seen an uptick in residential solar adoption after these large-scale installations were added to the community? Yes, we could add to that. Has anyone seen an uptick in residential or commercial storage adoption after these large-scale installations?
Good question for Galina, I think, and OE Solar.
We normally see an uptick of people interested in them. It doesn't always mean that they actually purchase them because the cost constraints are still an issue on residential projects for battery storage. But once you see something like this go in the community, it is something that people start thinking more about, and it is something that they look into more.
Yeah, I would also add that we've participated with Sandia and DOE on a large number of these demonstration projects at this point over the years. And one of the things that happens is that the utility generally becomes much more familiar with energy storage through having to, participate, because whether in a lot of cases, the utility is a partner, even if they're not a partner, there's interconnection with the grid that has to happen. And so the utility has to become familiar with energy storage, how it's designed, how it operates, and so forth. And through that process, I think we've seen a number of utilities become more interested. And when the utilities become more interested, they do a couple of things. Sometimes they start to install storage or procure storage on their own. And they can also start to encourage and support their customers in doing the same thing. So I think it has an impact beyond just people kind of seeing what's happening and deciding to order a system, but I'm sure that does happen as well.
We can add to that in future, we will need much more energy storage because we will have to decarbonize our system and rely on solar and wind and other renewable sources. And those are variable and they need storage. So huge amounts of storage will be necessary in the future.
Here's somebody who's asking, how does this type of system or this model work in situations where you can't charge the battery from the grid?
Well, our Navajo system doesn't charge the battery from the grid. It charges the battery directly from the solar input from the photovoltaic panel. It's completely isolated, completely independent of the grid. That's why it's a remote application. And so if you're asking how does this work in a remote facilities? Yes, it's nicer to if you're connected to the grid, because then you don't then you have enough background for a longer period. But if you're off grid and you are providing your own basic energy from solar and photo or from wind or whatever, then that's your input, and the variability is taken care of by the storage. After all, by its very nature, photovoltaics doesn't provide you energy at night. So that's why you want to have your storage.
Yeah, and I would add that for a long time, there were situations where people had grid access but still couldn't charge from the grid, because in order to qualify for the federal investment tax credit, which was tied to solar, they had to charge only from solar, or at least a large percentage, most of the time, from solar in order to qualify for the credit, at least for the first 5 years, and then the credit would be depleted, start charging from the grid. That's no longer the case, because we now have a standalone, finally, after a lot of people working hard to get it, there's finally a standalone federal energy storage tax credit that doesn't tie the storage to the solar in that way. So presumably there are situations where people can now run their storage more flexibly and do things that they might not have been able to do if they had been restricted to charging from solar on site.
I'd like to throw a quick question at Henry on this topic. Do those standalone systems run purely off of solar during the day if available? They don't use the battery at all? I mean, is it mostly solar until it's needed battery? Is that how it works?
Yes. So, what the house sees is just power supplied, but how the system works is that the PV current will supply the house, and if needed, it will charge the battery. The charge controller is in charge of that. But if the battery's not charging, then the PV current is supplying the house until there's not enough PV to do so, and then the battery makes up the difference.
Remember, you have clouds.
Yes, that too.
Yeah, and any interruption like clouds or people walking by or whatever creates shade on the photovoltaic unit is taken care of by the battery. Those are the short-term interruptions, and then of course there's the long-term interruption of night.
When we started this work, really, we started, we greatly expanded our work in storage right after Superstorm Sandy in 2012, and which hit the East Coast hard and knocked out power in some areas for weeks. And one of the things that was really odd about that whole situation was that we were getting calls from state energy agency members, because they were getting calls from customers who had installed solar, often with state incentives. And the customers were calling up saying, why is my solar not powering my house now that the grid is down? Why can't I turn my TV on? Because I have solar, what happened? And so they were having to explain, and this is, people just didn't quite understand. That should have been explained, obviously, by the installer. But that without a battery, your solar isn't going to function during a grid outage at all. It's going to shut off because that's how it's designed. Otherwise, you're back feeding power up the line, and you're going to shock some poor power line repair worker who's on a pole somewhere. So what you have to do is, under that circumstance where the grid is off, have a way to separate, it's called islanding, from the grid. You separate your system, and then if you don't have the battery, your solar is still not going to function because, as Emery said, there are clouds and there's nighttime, and you can't run electrical equipment, sensitive electrical equipment, on power that's fluctuating up and down and on and off constantly, it's going to do damage. So the battery kind of smooths all that out and makes it work. Sorry for the 101 there. I just felt like I should jump in with that. Okay, here's a comment, but I guess it's something that we might want to address. It says, this fellow says, not all lithium batteries are the same. Fires are commonly caused by batteries with cobalt. Non-cobalt batteries, such as LFP, which is an iron phosphate chemistry, do not have the same issues and are also certified to UL 9540A. LFP does not require venting, does not require cooling systems. I'm not sure that all of that is entirely right, but I think there are some interesting and significant differences. Anybody want to address cobalt lithium batteries?
Well, point well taken. Some batteries are much more prone to fires than others, and some are much safer. I believe they are not necessarily entirely without need of fire suppression systems or
Cooling.
air conditioning systems, but much less so than some of the other lithium systems that contain cobalt. Of course, cobalt has another reason why we want to avoid it, is because it is much more well, it also has supply chain issues that are difficult.
Okay. Well, we're at the end of our time. I want to thank everyone who attended and also everyone who presented. This has been quite informative, and if we could, there we go, give everyone a preview of some upcoming webinars, and then we'll sign off.
Yes, thank you for that intro, Todd. I just wanted to highlight there's a webinar coming up on December 16th. That's the last one on this list. That's our next STAP webinar, and it'll be focusing on the new federal money coming in from the Inflation Reduction Act. We have an all-star set of presenters from different DOE offices. Dr. Zook is going to be joining us for that webinar as well. So I'm very excited for that one, as well as I will be tuning into the 3 webinars that will be happening before then as well. So please go to our website, cisa.org/webinars, if you're interested in signing up and attending any of these upcoming webinars. And again, that is the website that will also be posting the recording and the presentation slides and everything from today's webinar as well. So like Todd said, thank you all for joining us today. A huge thank you to all of our presenters for sharing their work and their projects and a bit of a sneak peek into their world. So thank you all so much, and we hope to see you at future webinars. Goodbye, everyone.
Bye-bye.
Thank you.